So we said that with state diagrams, right? With state diagrams, which we tried to demonstrate earlier on, state diagrams. We said that state diagrams, you don't want to create state diagram for every class that you write, because in fact, most classes, hopefully, don't have an interesting behavior. Basically, they just retain a set of data, which which sometimes could be an invalid state. So you can still describe some sort of like invariant states in them, but they really don't make a lot of transitions. They basically, your desire is to keep your object in good state at all times, and it's just the only state you want to keep it on. Would you want to build a state diagram for that type of thing? No, because your diagram really looks like this, right? So your state diagram is just this, right? You just want to basically all you want to do is that you want your object to be in use, and then it basically goes to the final state that is no longer being in use, right? So that's your state diagram for many classes, right? Just basically creation, use, and exit. You don't want to draw a separate state machine, design state machine for just this single state. That's just not what you want. So you want to pay attention to objects with interesting behavior, complicated states, and certain rules that you want to follow to transition from one state to another. Likewise, with activity diagrams, what you want is that you want to model processes that have an interesting, interesting details. You want to basically validate attempts to implement certain processes by showing something readable to the user. But again, it turns out that with all kinds of forks and joins and decision making, people quickly get lost. Even expert users that know really well and can write a lot of complicated Excel spreadsheets, they kind of quickly get lost in the environment of activity diagrams. So keep them brief, don't overcrowd them, but they can obviously be used to visualize interesting processes, especially when there are parallel elements. And this one again, this is the element that creates the split to parallel threads, and this creates the join, right? Now it's interesting to note here, this is that let me show you this, right? So say that this is a thread of execution, and I will show it as blue, right? So this is a blue line, this is a blue line. Where does the blue line go, right? We don't know from this state diagram, but it could go over here, right? So this is like a blue line, execution continues on over here, and this is blue, and it comes in right here, right? Comes in right here. And this can be like a green line over here coming out. So this is a brand new thread of execution, right? So what happens here is that, although you have the disjoint or fork, split into parallel processes, is that over here you just created new thread of execution, whereas this one continues on the same thread of execution. Okay, so this thread could go right here, and guess what? This line, what color is this line? It can be blue, right? You can just continue using the blue thread and exit out on the blue thread. And what happens then to the green thread? It terminates over here, right? So it terminates. Obviously, this is not standard UML, but just to show you the relationship between the threads, okay? Or you can do something like this. You can basically terminate the blue, let me switch over to the blue color, right? So terminate the blue thread over here and continue on the green one to exit the activity, right? It's also possible. Both variations are possible. So the join really doesn't tell you, doesn't give you the true picture which thread does what, right? So this coloring, sometimes you can use different types of connection lines to indicate those things, but and again, it should be noted that of course this is the same thread. It goes either through this branch or through this branch, right? But it's still the same thread that comes through either line, right? So again, formal diagram, just like we had at the beginning, without any kind of indication of one thread of another, doesn't tell you which one is which, because the accent, the emphasis is made really truly on the fact that there is parallelism, but not any detail on which way it goes, because it can be implemented multiple ways, and it can even be done differently depending on internal conditions in the system. So it's all this is way too abstract to represent oftentimes directly in the software. So I think for software developers, they just, it's a good overview of a process, but it certainly is not an immediate solution, right? Because, for example, a sequence diagram like this, when we do the analysis, it's very direct, right? It shows an actual objects participating, calling each other's methods or sending messages to one another. It's very directly corresponds to objects, which is very directly can be written very directly in software. Whereas activity diagram is much more vague. It's much more high level, and so therefore it can be confusing. So the weaknesses of it is that it can be confusing to end users, but without a lot of details, it's not helping a lot the developer, because they still have too many questions regarding how exactly to do this. So again, the solution is to write the plain description of the problem, right? Just write down what has to happen. That's the most important part in many cases, right? So just really a written description still cannot be replaced by just magic of diagrams. They look good, but they don't answer all questions for all audiences. So just again, we can just we'll already sing all of this. So we have decisions and merges. We have when we make the decisions, we say that we have guards. So in UML, what we do is that these conditions that become true, they basically do it like this. So when we have a symbol that represents a decision split, right? So sometimes you can indicate a condition, right? And the condition comes in square brackets. And on the other side, you can simply say else, right? Or otherwise, right? Otherwise, do this, right? So you can have condition and else means that condition is not true, right? So you're coming in over here and you're exiting upon whether condition is true or not, and you continue with your other type of activity. So that's what this slide highlights there. Now, there's also an idea of swim lanes, and again, let's go through the demonstration. The same thing, okay? The same thing or similar thing, process, order, activity, over here is displayed with the vertical separation bars, which essentially create, and let me also make a copy of this, and we can do our demonstration for this next set of ideas for activity diagrams. Right, so we have this demo of